Welcome back. This is the next episode in our off-highway vehicle design series. Today it's about fluid power, but not so much the details of how to make it work, more an overview as to some of the things you need to be aware of when you're working and designing with hydraulics and pneumatics. So there's a lot to think about when doing hydraulic circuits and pneumatic circuits. And this video is intended just to give you a few hints as to what to consider. And we're going to start by talking about open loop and closed loop hydraulic circuits. So this is a diagram showing open loop and closed loop. Let's look at the open loop first. Pump and motor, could be an actuator, but pump and motor, drawing oil out of the oil tank, doing its job and returning it to the oil tank. There's no real loop, or the loop is via the oil tank, which is open to atmosphere. Closed loop is more a consideration with pump and motor combinations, and it essentially means that the oil stays in the loop between the pump and the motor. And it looks quite simple and straightforward, as you see here. In reality, there's leakage flows that have to be made up there, and here's a charge oil pump right there to do so. But you've also got filtration and cooling. And as simple and nice as this hydraulic circuit is, it's never that simple in reality. So since we're talking about pumps and motors, let's look at some different types. Here's a gear type. Two gears that are meshed together, taking oil from one side and squeezing it out the other side. They're great pumps and motors. They work reliably, they're fairly dirt tolerant, they're rugged and robust and last forever. And they're fine to use. Another type is a vane type. And here's two versions of that, one with sliding vanes and one with flexible vanes. If you know what a Jabsco pump is, you'll know that it's a rubber pump with flexible vanes like this, and it uses the fluid that is pumping to lubricate it. The sliding vane has rigid vanes, but they're in a slot. These are good, not quite so tolerant to dirt, not quite as robust, but for simple circuits and applications, they're fine. And here's the granddaddy of them all. This is a piston pump or motor. Now, essentially what's happening is there's a number of pistons running in their cylinders, pumping oil. Those pistons have a ball end attached to a swash plate, which is similar to an arrangement on a helicopter. The angle of that swash plate is varied by an actuator, and that means that the stroke of the pistons is varied. So hence variable speed pump or motor. There are fixed types, but for this discussion we'll just look about variable arrangements. Really good, great pumps do fantastic things until they don't. They're generally relatively complex units in relatively complex hydraulic circuits. So that's it quickly for pumps and motors. I'm not going to talk about compressors for air because basically everybody's had some experience with them. They're either piston type or screw type, and they just basically work simply. I do want to talk about what connects all of these components together. Pumps and motors and actuators and so forth. And that's typically hose or tube. Tube is generally used where it's protected and it's unlikely to be damaged and therefore unlikely to need to be replaced. If you're running a line from the left side of a vehicle to the right side of a vehicle through the chassis, you'll probably make that a hydraulic tube and then put a hose on each end. If you run it as a hose all the way through, it's going to be very difficult to thread through a replacement, hence tube. Now, what's involved in a hose? The rubber bit, except it's not just rubber. There's a lot of reinforcement. There's different ratings, different types. It's fraz, hose, and so forth. But generally speaking, for hydraulics, certainly, there's a hose end on each piece of hose. So let's look at a few of those. This is just a selection of hose ends. Again, there's a variety from push-on and swage, screw-on reusable fittings. I've used those on drill rigs, for example, so that if the drill rig blows a hose in a remote area of the country, if they're carrying a spare bit of hose, and this is a good reason to standardize on hoses, they can cut the new piece to length, take the fittings off the blown bit of hose and reapply them to the new hose and keep working. They don't have to stop work and go hundreds of kilometers to get a new hose or a new fitting. So we've now got a bit of hose with a connector, a hose end. That basically never connects to what you need it to connect to. There's always an adapter. 45 elbow and 90 elbow, a straight, a reducing bush, a straight adapter to go from one size to another. There's a multitude of different things, and you can generally make up just about match anything with anything. The difficulty is in different thread systems though. If you're British or British based, it'll be BSP. If you're American based, it'll be NPT. They're very close, but they're not the same. And it makes it difficult if you've got an American engine and a British transmission. One's NPT, one's BSP. Don't bother trying to find an adapter. They don't exist. The adapter is a bit of hose with a JIC fitting. And you go from NPT, JIC and an adapter, down the hose and JIC, a BSP fitting on the other end. It's frustrating, but that's the way it is. JIC is from memory Joint Industry Council, and that's it's a flared fitting, and it seals on the flare where the others seal on the thread. There's also SAE type fittings and O-ring fittings and so forth, but they're for higher pressure specialized applications. So if you're playing with NPT and BSP, you'll also get into whether it's taper or parallel. Now, the general rule of thumb for pressure fittings is the male is a taper, female is parallel. So you will have a BSPP, British Standard Pipe, parallel, female, and a BSPT, taper, male. Similar arrangement with NPT. People get very confused about it. Yes, you can have parallel male threads, but they're not generally used for fittings for pressure. They are used for things like pipe handrails. So just be aware, get your tapers and your parallels right. For pneumatics, things are simpler. I like to use pneumatic tube because it's just fantastic. I don't need a hose end. I can cut a tube to length and stick it in a fitting. And I'll show you what I mean. This is an array of fittings, in some cases valves and flow restrictors that are already fitted with connectors. To connect here, you push the tube in. The tube is nylon or polyurethane. Again, different sizes, different colors. The color coding is great if you want to use it. You can have a different color for each subsystem. But you just push it in and it locks. You can't pull it back out because of that collet. If you want to pull it back out, you push the collet in and then pull the tube out. It's simple. It's really easy to assemble. It's fantastic for prototyping, but it's also prone to sabotage. It's very easy for someone to swap hoses on you and cause a problem. So now we get to a little bit of reality. Hydraulics are fantastic right up until the time they aren't. They're very susceptible to poor maintenance practices and in particular dirt. You're running piston pumps and motors, dirt and contaminants are a nightmare. Because once you've got particulates in a system, you will never ever get it out. And this happens when you let things go too far and you disintegrate a pump or a motor and the debris goes all the way through the system. It also happens when you didn't clean the hydraulic tank out well enough when it was made. And it happens when you didn't clean the hose assemblies out after they were made too. A little bit of rubber goes a long way in blocking ports and stuffing up valves. So you need to make sure everything is very clean, particularly if you're using piston pumps or motors. For simple systems, use a gear pump and go open loop. For more complex circuits, you're going to get into piston motors, piston pumps, and probably both variable. For a vehicle, you then have to worry about how you do a differential function and a nose spin and lock up and all that sort of stuff. There are also rotary actuators available that will take you part of the way, and they're fine too. But you need also to be aware that, again, particularly with piston pumps and motors, you're running with high pressures. So you've got a personal risk as well. Hose bursts or leaks, or someone in maintenance undoing a line that's still pressurized can lead to fluid injection, and that's a big problem. In most cases in Australian mines, fluid injection is a helicopter ride to the hospital. Now, pneumatics work off all the same principles, obviously lower pressures, lower power, lower risk. They're just simpler, but there's still some traps. One of the ones that I see people fall into all the time revolves around lubrication. Industrial type equipment is generally designed to be lubricated, and you might have a filter regulator lubricator unit just after the main air tank. Vehicle systems rarely need a lubricator, and it's quite common for people to assume that a lubricator is required. And that can end up with problems because you've got fluid connecting in valves, collecting in valves that were never designed for it to be there. So be careful of that as well. If you're going to use hydrostatic drives for a vehicle, that's great. Plenty of people do. You've seen my hydrostatic Ventrac tractor in previous episodes. Works magic. But only ever use hydrostatic drives where there's no other practical solution. They are definitely more susceptible to damage, more costly to repair, and more complicated. If there's a mechanical drive option, use it. For cylinders, and I'm not using the word ram because the ram's a male sheep, for hydraulic and pneumatic cylinders, well, hydraulics and pneumatics are ideal for those things. Linear action, lots of companies doing automation with grippers and all sorts of attachments. Really simple to do complex things now. But you need now, in recent times, to stop and think about whether fluid power is the right solution. Fluid power systems bring with them a lot of baggage. Tanks, compressors, pumps, filters, all that sort of stuff. A lot of smaller loads now can be taken with linear actuators. And I'll give you a quick example. You may have seen this earlier. Here's Bobcat's new Rogue X. There's also a cabless version, a remote control version. There's no hydraulics on that. It's completely electric, including the lift. So it can be done. Now, I'm a mechanical engineer. I trust hydraulics long before I trust electrics. But in the right application, electrics is a lot simpler and you can do a lot more things with it. You just can't fix it yourself. Pneumatics are a lot easier to troubleshoot. Now, the hydraulic or pneumatic decision might be somewhat taken away from you if the engine is air start. If that's the case, you've already got compressor and tanks and valves and so forth on board. So the logical thing to do would be to try and do the other functions with pneumatics. When you're designing, think about the standards that are applicable. Now, there's not so much for the actual circuitry itself. If you listen to our brake video, we talked about making things fail-safe and functional safety. Should be considering that here too. Safety is a big thing with fluid power systems, particularly if there's a level of automation. But where I see people get trapped a lot is hoses. They ring up their local hose supplier or mate and get him to come and hose up a machine. And then 2 months later they realise that, there was actually legal requirements or regulations around those hoses, safety factors and all sorts of things. And they've got to now re-hose the machine. Work out your standards before you finalise your design. Make sure your hoses, not your valves, not your fittings, your hoses are right for the application and meet the regulatory requirements. So that's a bit of a choppy review of fluid power. I'm not intending to tell you how to design the circuits. I am intending to tell you what's available and what to watch for. Pneumatics are easy. They can do amazing things very simply. But they can't transmit high power. Hydraulics can. And as long as you manage the risks, it shouldn't be too big a problem. But there are very rarely small problems with hydraulics. They usually work up until something expensive is broken. But often they're the only practical solution. Go through your fluid power systems. Make sure they're as simple as you can make them and still do the job. Make sure everything is clean, particularly if you're in an export market. I used to send a lot of aircraft towing tractors to China. We did not want warranty calls from there. Make sure everything is clean and reliable and it will last forever. Similarly, make sure your circuits are safe, fail-safe if need be, if appropriate, and easy to maintain. And when you've got all that sorted out, move on to the next stage of your design.